last mini-topic video, we covered fields in general. We identified that a field is just a construct, meant to model how one thing can act on another thing, that is, produce a force, at a distance, due to the internal properties of the two things. We briefly touched on the three types of fields that you'll cover in Unit 3, Area of Study 1, namely gravitational, magnetic, and electric fields. From now, I'm going to assume that you understand that those fields arise from the internal properties of objects. Now, the temptation in learning about these three fields for the first time in VCE physics is to separate them, to think about gravitational, magnetic, and electric fields as completely different topics. Although we'll soon focus on each field in more detail one at a time so that we can properly cover the specific ideas of each, the ultimate take-home message here is that understanding these fields at a conceptual level will lead to much better and cohesive knowledge of the entire area of study. In this mini-topic video, we're going to look at gravitational, electric, and magnetic fields in more detail in order to compare and contrast them. Let's kick it off with some notation. Gravitational fields are denoted by the lowercase letter g, because capital G is reserved for the gravitational constant, and electric fields use a capital E. And of course, following from this, magnetic fields use the capital letter B. Wait, what? Why B? Well, it simply comes down to the notation used by Scottish scientist James Clerk Maxwell, who brought together the concepts of electricity and magnetism into a coherent theory of light, or electromagnetism. You may have seen those t-shirts with a bunch of equations on the front and the phrase, "Let there be light." I'm not really sure if understanding that t-shirt makes you cooler or not, but now you know you can't unknow. Sorry, you're part of the problem now. As these fields are vector fields, you may often see them in other sources, written either in bold font or with an arrow on top of the letter, which is just a convention to tell the reader that we're dealing with a vector quantity. And forces due to these fields are often denoted using subscripts, so capital F, subscript lower g, capital F, subscript capital E, and capital F, subscript capital B, which is just something to keep in mind when you look at other sources of educational material which may or may not be VCE specific. We touched on vectors briefly last mini-topic video. Electric field lines point in the direction a positive charge would accelerate if dropped in at that position. So lines point outwards from a positive charge, for example a proton, because a proton repels a positive charge, and they point inwards for an electron, because an electron and a proton attract. Magnetic field lines always go from a north to a south pole, or in the direction a north pole would accelerate if dropped in at that position. So vector field lines point out of and away from north poles and into and towards south poles. Again, opposites attract and like repel. Gravitational field vectors always point towards the mass producing the field, because gravitational fields are always attractive in nature. Wouldn't that be nice? So we can imagine putting a tiny test mass, which amusingly we have to imagine actually has pretty much no mass, to see which way it would accelerate from that position. It needs to be tiny and negligible in mass so that it doesn't affect the gravitational field of the object under investigation. As a reminder, the vector arrows just represent the field at that position, with the direction represented by the point of the arrowhead and the tail length proportionately representing the size or strength of the field. Now, remember, the field is everywhere, not just on the drawn-in arrows. Theoretically, you could draw an arrow at all the infinite points around the object to represent the continuous field. When you are drawing a field around a point source in VCE physics, it's highly recommended that you use about 8 arrows equidistantly spaced. Also, remember, this is a 2D representation of a 3D field. Remember in year 11 you covered vector addition, probably for contact forces? Well, Let me give you an example. If Trent and Neve are fighting over a banana, and Trent applies a force of 3 Newton to the right, while Neve pulls on the banana with a force of 4 Newton up. The resulting force will be 5 Newton up and right. Simple trigonometry should yield an angle of 53.1 degrees to the horizontal. The same thing happens with field vectors. So if you have 2 protons or a proton and an electron, for example, the resultant vector field at any point is the vector sum of the 2 fields. Common magnetic vector fields you will see include bar magnets and horseshoe magnets, but you could also imagine 4 bar magnets arranged like this, for example. Unlike gravitational and electric fields, however, you will never see a single magnetic pole. Magnetic fields always have a north and a south pole. That is, they are dipolar. We will discuss monopoles more in the next mini-topic video. Here you can see that the magnetic field direction at each point around the magnets is the vector sum of the north and south fields. Knowing the direction of the resultant field is important, as this will be the direction of the force applied to an object placed in the field at that particular point. The size or magnitude of the force at that point follows the same general rule you would have come across in motion in Year 11 physics, and is composed of the thing being actioned on and the thing forming the action at that position in space. Check out this fantastic summary table. If you've been playing along at home with this video, you should be able to anticipate the table entries. If not, it's a great way to test your conceptual understanding when the time comes around to revisiting this area for your pre-exam studies. You'll notice that the force on an object due to a field is clearly composed, in all 3 cases, of the field, so G, E or B, acting on the thing, so mass, M, or charge, Q. You'll note that for magnetic fields, there's an extra term in there, velocity. This should not come as a surprise to you. Why? Because of course, magnetic fields arise from moving charges. So the thing being actioned on by the magnetic field is described by both its charge and also its velocity. This has been Red Lipped Astro with a comparison of fields. If you found this video helpful, please feel free to like and subscribe. There's also room for comments and questions underneath. Thank you.